process going, what should I really do? If I want to have a good absorption process going, what should be the condition, what's the necessary condition for me? With regard to the population difference. Should I have a large population difference or a very small population difference? If I have a large population difference, my absorption will beat stimulated emission. I will therefore see an absorption going. So at any time I want good absorption, I really need a big difference in the population between the ground state and the excited state. Now you see where I'm coming from. If I have a large population differential, absorption is a dominant process. If the population difference is not very large, it's nearly equal, I really don't see much absorption. In the limit, when the two populations are equal, I don't have any absorption in the first place. Therefore, if I want to see an absorption, what's the first thing I must do? Ensure I have a lot more molecules in the ground state than I have in the excited state. Coming back to the NMR experiment, if I want to have a lot more molecules in the ground state, then in that state, what should I do? I must pull those states apart. If I pull those states apart, then there will be more here and less here. I have a decent absorption to actually measure. If these two states are very close to each other, what happens? There's not a big difference in population. If there's not a big difference in population, I don't have an absorption experiment. I want a large population differential, and therefore I want this field to be large. The field is large, I can split these levels. If I split these levels considerably, then I have a large population differential, and then I have a successful experiment. I'm making it so dramatic, but even in this 10, 100, 500 or 600 megahertz machine, the population differential is not so great, but it is enough for the experiment. The point I'm trying to make is, compared with the 100 megahertz machine, the 600 megahertz machine gives me a larger population difference, and therefore a better absorption spectrum than what I would have with 100 megahertz. That's the reason why NMR people have kept on increasing the magnetic field of the machine. But when I increase the field, I create a bigger separation, a bigger population differential, a better absorption spectrum, more sensitive absorption spectrum, and therefore a better experiment. That's the reason I said in the 60s and 70s, 60 megahertz was the order of the day. It went to 100 megahertz. And where did it break through and start getting all these 200, 300, 400 and so on? Two things had to happen. First, we had to have a strong magnetic field. We had to have strong magnets. And strong magnets came into the picture after we got superconducting magnets. So we had to wait for advances in superconducting physics before we could get very strong magnets. And once we got that, of course, today we routinely have all these things. That's also the reason why if you go to the NMR machine and you ask them what are the things that you need to keep in stock or what are the things you need to get to keep the machine running, they need liquid helium, liquid nitrogen. Why do they need liquid helium? You got to keep your magnet in place. You know, the superconducting magnets, material is not superconducting until you get to very low temperature. So you need liquid helium to keep your magnets the way they should be. And of course, liquid nitrogen is also required to keep the liquid helium from going away, as a secondary fortress around that. So you need cryogens. You really need cryogens. That was one thing that was required. The other thing that was required was, in the later stages, NMR was not just the way it used to be done earlier, and you will see how it was done as we go along. In came the new technique called Fourier transform NMR. You have Fourier transform IR, which you're using all the time. And what does the Fourier transform IR do? It collects data and very quickly does a Fourier transformation and gives you the spectrum. The same thing in NMR, and you will see that the two are very parallel. Here you collect data in some manner, take the data, do a Fourier transformation, and lo and behold, you have an NMR spectrum. Now you have to have a bunch of computers which could do the Fourier transformation extremely fast. There's no point in saying that Fourier transformation is very advantageous if it were to take you like 2 days to get the Fourier transformation done. You give your data today, come back on Monday, and then you get your data. No. You have to have the Fourier transformation done immediately. And so you have to wait for advances in computer technology. So all these big NMR machines really were looking for, were waiting at, I would say, for two big advances. One, advances in superconducting physics, and another, advances in computer technology. And once these two came, it just seemed to be just right for these machines to grow. And Today you find 100, 200, 300 is all gone. The least you can buy is a 400 megahertz machine. You can buy 5, 6, 7, 8, I believe you can go up to 1000, which is a gigahertz. And you will see that there are advantages in going to bigger and bigger field machines. Because when you go to bigger and bigger field machines, there are certain resolution issues that can be sorted out, which is very important for biologists, particularly when you look at large molecules, looking at proteins, looking at polymeric substances, and you want to get the information about the structure. You need these very large field machines, and that's the reason why it's used. If you are a chemist, you just synthesize the compound, and you want to know what the structure is, NMR, you will see, actually they are doing very unambiguous method what the structure is. 400 megahertz is more than adequate. In fact, 200 megahertz would be more than adequate for such applications. The problem is you can't buy one today because nobody makes them. The minimum that you get is a 400 megahertz. But to do biology, particularly large, even in chemistry, if you're a polymer chemist, and you're looking at large polymers, and you want to study these conformations and structures of large polymers, you need high field machines. I'm just throwing this information at you, but then we will see very soon as to how these things are really done using these high field machines. First, we will look at simple molecular structures. We will look at ethanol, we look at methane, we look at acetone, and see how these structures can be delineated using NMR. And I'll tell you right now, the sort of questions that you will get in the exam and what you must prepare yourself for. I'll probably give you a bunch of NMR spectra. I'll give you a bunch of IR spectra. I'll give you a bunch of compound names. And all you have to do for me is to tell me, this NMR looks like NMR for a compound whose IR spectrum should look like this, and that must be the compound. Basically, you must be able to figure out which goes with which, which goes with which. You don't have to remember anything. All you have to do is pattern recognition. And if you know how to look at these things, what to look at. Of course, in IR you know, right? 1700 units a carbon, 3000 units an OH, 1030 or 1020 units, T second bond. You know all that. If you don't know all that, piece of paper, write all that. You know. So I think I'll stop here. And now I want extra day. When do we do it? So Friday is the class, but I need 2 extra days because next week